Howdy. So what have we learned so far? We've learned that entropy is best thought about in terms of per Dr. Boltzmann's famous equation. Entropy equals Boltzmann's constant times the natural log of W, where W is the number of configurations. Now, when we're talking about configurations, we could be talking about positions of atoms or molecules, relative orientations of molecules, ways of filling energy levels. Now, we can go from these three different types of configurations to think about systems. So in terms of composition, the more atoms per molecule, the more energy levels, the higher the entropy. In terms of intermolecular forces, the stronger intermolecular forces, the fewer number of configurations for positions or orientations, the smaller the entropy. In terms of physical states, a gas always has higher entropy than the corresponding liquid, which always has a higher entropy than the corresponding solid. And in terms of temperature, higher temperature means more energy levels are accessible, and so that gives you a higher entropy. We've also seen that, according to the second law of thermodynamics, if a process will increase the entropy of the universe, then it is spontaneous. Spontaneous means not instantaneous, but it means occurs without any outside or intervention. Entropy is a measure of the number of configurations. The higher the entropy of the system, the more stable the system. Mixtures tend to have a higher entropy than pure compounds. And so this video is on colligative properties. Colligative properties are due just to entropy. So colligative properties enable us to calculate how boiling point, freezing point, vapor pressure change when a solute is added to a solvent, hence increasing the entropy. Osmotic pressure is also a colligative property. After watching this video, you should be able to describe how colligative properties are a result of mixtures having higher entropy. You should be able to describe how, for colligative properties, the only thing that matters is how many solute particles there are. What the solute particles are do not matter. And so we actually assume ideal solutions when we're talking about colligative properties. You should be able to calculate the change in boiling point, change in melting point, change in vapor pressure, and osmotic pressure using colligative properties. And so if we plot Gibbs free energy versus temperature, what we'd see is we have these lines, if we're assuming delta H and delta S are temperature independent, which under small ranges is pretty good. Now, the lower the Gibbs free energy, the more stable. And so at low temperature, solids tend to be more stable. High temperatures, gases seem to be most stable. Now, where the lines cross just correspond to a phase transition. And so for this crossing, you're going from liquid to a gas. At this crossing, you're going from a solid to a liquid. Now, the slope of G versus T is equal to the minus negative entropy. And so entropy is always positive for solid liquids and gases. And so that's why these slopes are always negative. Now, because the gas has the largest entropy, it's going to have the most negative slope. Because the solid has the least entropy, it's going to have the least negative slope. Now, because of the gas's entropy and it's the most negative slope, that's why gases are always the most stable phase at high temperature, as long as the compound doesn't decompose. And because solids have the smallest entropy and the least negative slope, that's why solids are the most stable phase at low temperature. Now, if we think about, here's a phase diagram, so we're plotting pressure versus temperature. And so this red line corresponds to the value of pressure for this diagram here. So as you start here and you increase the temperature, you go from solid to liquid to gas. And that corresponds again, solid being the lowest, Gibbs free energy, then the liquid, and then the gas. That's kind of interesting. We could also look at a pressure below the triple point. Just remember where three phases are equally stable, that corresponds to the triple point. You should also remember that the phase diagram indicates what is the most stable phase. It does not indicate what's present, right? So whenever you have a liquid, you always have a vapor. It's just in this region, the liquid is the most stable. And so below the triple point, notice that we're just going from a solid to a gas. And that's because the liquid is never the most stable phase. And so that's how you get sublimation. It's also kind of interesting. Most compounds, if you go below the triple point, you can cause sublimation. And so colligative properties are a result of increase of entropy due to adding a solute. They depend on the relative numbers of solute and solvent particles, not on the chemical properties of the solute or the solvent. And again, that means that we're assuming ideal solutions. An ideal solution, you assume that the solute-solute interactions, solvent-solvent interactions, and the solute-solvent interactions are all the same. So there's no change in enthalpy of solution. Solids are typically ideal solutions are often similar in composition and structure, and so they just have to have the same intermolecular forces as the solvent molecules. The lower the concentration, the more closely the real solution behaves like an ideal solution. And so if you're looking for, non-electrolytes, so 0.1 molar, typically you'll get an ideal solution. So electrolytes where you form ions, 0.01 molar for ideal solutions. So the solid has increased the entropy of the solution phase, decreased its free energy, increasing the range where it's the most stable phase. And so if you think about if you had a closed container with a liquid, solid, and gas, and you add a solute, the solute is going to go in the liquid. It's not going to affect the solid or the gas. And so here we're going from a pure liquid, and it's increasing the entropy, going to lower the Gibbs free energy. And so this is the Gibbs free energy line for the solvent. And so again, where these two lines cross, that corresponds to melting. And so what's actually happened is you've decreased the melting point. Now here we got the gas and again the liquid. Now adding the solute to liquid does not change the gas, does change the liquid. And so we've increased the boiling point. And so adding the solute to the solution, you've increased the boiling point, reduced the melting point, you've increased the range where the solution is the most stable phase. If we look at a phase diagram, and so this is for pure water, and then this is for salt water. And so again, you've increased the boiling point, you've reduced the melting point, so you've increased the range where it's the most stable phase. And so you've elevated the boiling point, you've depressed the melting point, you've also reduced the vapor pressure, and osmotic pressure is also a colligative property. Now it's kind of interesting, if we look at these, we have the vapor pressure of the solvent is equal to the vapor pressure of pure solvent times the mole fraction. For the change in the boiling point, it's equal to the von Hoff factor, a constant, times the molality of the solute. The change in freezing point is equal to the von Hoff factor times a constant times the molality of the solute. And then osmotic pressure is equal to the von Hoff factor times the gas constant times temperature in Kelvin times the molarity of the solute. And to me, it's kind of interesting. So here we're talking about vapor pressure in terms of mole fraction. Here we have molality. Molality is in moles of solute per kilogram of solvent. And for osmotic pressure, we use molarity, which is moles of solute per liters of solution. A little bit different. It's also kind of interesting, if we look at the boiling point elevation, freezing point depression, this constant K depends on the solvent, not the solute. And so nowhere in these equations do you see the identity of the solute, actually in any four of those. All that matters for boiling point elevation, freezing point depression, is actually the identity of the solvent. Now these bottom three have the von Hoff factor. The von Hoff factor is the number of particles per formula unit. And so if you dissolve sodium chloride, you'll get a sodium ion and chloride ion. And so you have 2 particles per formula unit. And so for sodium chloride, the von Hoff factor is 2. And so we need to know these different units of concentration. And so mole fraction of A is equal to moles of A over total moles. Molality, again, is moles of solute over kilograms of solvent. And molarity is moles of solute over liters of solution. Now, it's kind of interesting. Molality has the benefit of it being independent of temperature. Molarity will change a little bit with temperature because the volume of the solution will change. But you should know these three different units of concentration or measures of concentration. And so if we have a closed container and we increase the temperature, we're going to start causing more liquid to go into the gas phase.
A liquid confined to a cylinder, as shown here, with no other substances present, exerts a vapor pressure in the space above it. Molecules continuously transfer back and forth between the gas and liquid phases. The gas pressure in the cylinder represents the vapor pressure of the liquid that results from this equilibrium. As the temperature of the cylinder increases, the average kinetic energy of the molecules increases in both the liquid and gas phases. A higher average kinetic energy facilitates the escape of molecules from the liquid phase into the gas phase. At the same time, the rate of return of gas phase molecules to the liquid also increases. A new equilibrium point is reached at a higher gaseous vapor pressure. The increase in vapor pressure with temperature is exponential. In this equation, A and B are constants that differ from one liquid to another. The absolute temperature is expressed in kelvins. When we take the natural log of both sides, we obtain this equation. It tells us that a graph of log vapor pressure versus the reciprocal of the absolute temperature should be a straight line.
And so if you remove all the other air and then increase the temperature, all the gas in that container is just going to be from the vapor. And so you measure that pressure, and that gives you the vapor pressure of the gas as a function of temperature, and that is actually an exponential function. Now, the stronger the intermolecular forces, the lower the vapor pressure, the higher the boiling point. And so here we got water, we have ethylene glycol solution, and so ethylene glycol is actually antifreeze. Antifreeze increases the boiling point, reduces the freezing point, so hopefully protects your car engine. But by adding ethylene glycol to the water, you're increasing the entropy of the solution, lowering its Gibbs free energy, and that's why you're reducing the vapor pressure and you're increasing the boiling point.
At 30 degrees Celsius, pure water and a solution of ethylene glycol have nearly the same vapor pressure. As temperature increases, so do both vapor pressures. But when the vapor pressure of water reaches 1 atmosphere, ethylene glycol is at almost half that. Pure water boils at a significantly lower temperature than does the ethylene glycol solution.
And so you should remember that a solution boils when its vapor pressure is equal to the external pressure. And so if you have an open container, the external pressure is just atmospheric pressure, and so that's why the solution will boil when its vapor pressure is equal to the atmospheric pressure, which is 760 millimeters of mercury. And so with the ethylene glycol, you've increased the entropy, lowered the Gibbs free energy, and so you've increased the boiling point, and you reduced the vapor pressure. And so the vapor pressure of the solvent is equal to the vapor pressure of the pure solvent, that's what that circle means, times the mole fraction. And this is referred to as Raoult's law. And so because the mole fraction of a solvent is always less than 1, that means the vapor pressure of the solvent in solution is always going to be less than the vapor pressure of the pure solvent. And so what is the vapor pressure of water in an aqueous solution that has a 0.05 mole fraction of glucose at 80 degrees Celsius? Now this is the mole fraction for the solute. We need the mole fraction for the solvent. And so the mole fraction of the solvent plus the mole fraction of the solute has to equal to 1. And so if we solve for the solvent, it's going to be equal to 1 minus the mole fraction of the glucose. And so that gives us 0.95. And so the mole fraction for solvent is 0.95. We can find the vapor pressure of pure water at 80 degrees Celsius. And that gives us the vapor pressure of the solvent in the solution as 337.5 torr. What is vapor pressure of water in a 0.1 molals aqueous solution of urea? Urea is a non-electrolyte, which means the von Hoff factor is 1. And so again, we have Raoult's law. And the vapor pressure of pure water at 25 degrees Celsius is 23.76. And so we have to get the mole fraction of water. And so if we assume that we have a kilogram of water, we can assume amount because all that matters is the fraction. And so if we assume we have a kilogram of water, that gives us a 55.56 moles of water. We have 0.1 molal of the urea. And so if we multiply it by the amount of water, we get 0.1 mole of urea. And so the mole fraction of water is moles of water over total moles. And so 55.56 divided by 55.56 plus 0.1. And so that gave us a mole fraction of 0.998. Multiply that by the vapor pressure of pure solvent, and we get the vapor pressure of the solvent in solution as 27.71. Again, the vapor pressure of the solvent in solution will always be lower than the vapor pressure of the pure solvent. And so we saw that the vapor pressure is always lower for the solvent in solution, and we saw the boiling point is always higher. And so we can calculate the change in the boiling point by the von Hoff factor times the constant times the molality. And again, this constant depends on the solvent, not the solute. And so change in boiling point, von Hoff factor is just the number of particles per formula unit. The boiling point constant for the solvent, and the concentration of the solute in units molal. And again, nowhere do you see the identity of the solute. And for the von Hoff factors, if you're looking at methanol, it doesn't break apart. It's a non-electrolyte, and so its von Hoff factor is 1. For sodium chloride, when it dissolves in water, you get a sodium ion and a chloride ion, and so you have a von Hoff factor of 2. Calcium chloride, you get calcium ion and 2 chloride ions, so you have a von Hoff factor of 3. And so calculate the boiling point of a 4 molal ethylene glycol water solution. The Kb for water is 0.51. Again, that constant is for the solvent. And so the change in boiling point is equal to I kbm. Ethylene glycol, non-electrolyte, and so the I is 1. Our constant for the solvent, 0.51 degrees Celsius molal. Remember, change in temperature in Celsius equals change in temperature in Kelvin. And then molality is 4. And so we get a change in boiling point of 2.04 degrees Celsius. So water normally boils at 100 degrees Celsius. And so for this solution, the water should boil at 102 degrees Celsius. And so again, we've increased the range where the solution is the most stable phase. We've also reduced the boiling point. Again, we've increased the range where the solution is most stable phase. And so we've reduced the freezing point. Now, the change in the freezing point looks very similar. It's equal to the Hoff factor, a different constant. Again, this one also depends on the solvent, times molality. Now, you got to remember the freezing point goes down. Typically, we neglect the minus sign here, but the change in the freezing point is always negative. And so we have freezing points, boiling points, Ks and Ks. Again, you should see this table in your worksheet. You may need these numbers on your lecture assignment. So calculate the freezing point of a full mole ethylene glycol water solution. The KFP for the water is minus 1.86. Again, sometimes that negative is in the table, sometimes not. Just remember that the change in the freezing point is always negative. Now this is the same solution that we calculated the change in boiling point and saw the change in the boiling point was 2. And so here we're calculating change in freezing point. And so again, ethylene glycol is not electrolytes, so electrolytic, so it just has a von Hoff factor of 1. This is our KFP, and our mole is 4. And so our change in the freezing point is 7.4. And the change in boiling point was 2. And so for pure water, it's the most stable phase from 0 degrees Celsius to 100 degrees Celsius. For this solution, the solution is going to be the most stable phase from minus 7 degrees Celsius to 102 degrees Celsius. So adding the solute, adding the ethylene glycol, increased the entropy, lowered the Gibbs free energy, increased the range where the solution was the most stable. Again, von Hoff factor is just the number of particles per formula unit. So for sugar, von Hoff factor is going to be 1, magnesium oxide 2, and potassium fluoride will also be 2. So you could be asked to put these in order of increasing boiling points. And so again, the more particles, the higher the entropy, the lower the Gibbs free energy, so the higher the boiling point. And so you need to find out the von Hoff factor and multiply that by the concentration in molality. And so aluminum fluoride will have a von Hoff factor of 4. And so that means the von Hoff factor times molality gives you 0.4. Magnesium chloride would have a von Hoff factor of 3 because you get 3 particles per formula unit. That gives you 0.9. Sodium chloride has a von Hoff factor of 2, and this is an organic, and so it doesn't break apart, and so it has a von Hoff factor of 1. And so I times M, so we see that the magnesium chloride has the largest I times M, and so it should have the highest boiling point, and the aluminum fluoride should actually have the lowest boiling point. And so again, remember I times M if you're comparing different solutes. And so it's kind of interesting. The concentration is a little bit different, right? Sodium chloride has a higher concentration, but because magnesium chloride has a larger von Hoff factor, the magnesium chloride actually has the higher boiling point. And so osmosis is also a colligative property. It's also a result of solute particles increasing the entropy, reducing the Gibbs free energy.
This membrane separates pure water on the left from a solution of sucrose and water on the right. The membrane is semi-permeable. Water can cross it, but sucrose is too large for the membrane's pores. Water molecules will move from a solution with a lower concentration of solutes to one with a higher concentration of solutes. A solution with fewer solutes has more water molecules that are free to move about and follow their concentration gradient across a membrane. Thus, there will be net movement of water across this membrane from left to right. This diffusion of water across a membrane is called osmosis. Osmosis is of great importance in the water balance of all cells.
And so again, in this membrane, the pores are small enough that water can go through, but the sucrose cannot. Now the sucrose is the solute and is increasing entropy, lowering the Gibbs free energy of the solution. And so the water wants to go to more stable. And so that's why you get a net transport of water from left to right. So you're always having transport from right to left and left to right, but you have more transfer from left to right because of osmosis. This is another picture. And so again, more solute particles, higher entropy, lower Gibbs free energy. And so this is the solution where you have the solute plus the solvent. Here we have the pure solvent. And so by having the solute, you have a higher entropy, which means you have a lower Gibbs energy, and so it's a little bit more stable on the right-hand side. Osmosis of a solvent from low concentration to high continues until you reach isotonic solution, which means that you have the same concentration. And so a cell in isotonic solution is fine because you have the amount of solvent going in and going out is the same. Cells in a hypertonic solution, the level of salt in the plasma is too high, and so you have solvent going out of the cell net. I mean, you always have both directions, but if the salt solution outside is too high, you have a net flow out of the cell, and the cell will actually collapse. If you have a hypotonic solution, means your concentration of salt inside the cell is higher, and so you'll have a net inflow of the solvent into the cell, and the cell kind of explodes or ruptures. Now, osmotic pressure is actually the pressure due to this difference in concentration. And so here we have a membrane, a tube, and we have a 5% sugar, 95% water solution in the middle, and we have pure water here. And so the pure water wants to go in the solution because it's more stable there. Now, at some point, the pressure from raising this level is going to counter the osmotic pressure, or when the pressure of the weight of the water is equal to osmotic pressure, then there will stop being a net inflow of the solvent molecules.
When a solution and a pure solvent are separated by a semi-permeable membrane, solvent can flow in both directions, but the solute cannot. Here, pure water moves into the solution, working to bring both the solution and pure water to the same concentration. This process, osmosis, continues until the flow of water across the membrane is balanced by the pressure exerted by the water column.
An acidic sucrose solution containing methyl red indicator is poured into a semi-permeable dialysis membrane bag. The indicator is red in this acidic solution. The membrane bag is immersed in a neutral solution. The solution inside the membrane turns yellow as the neutral liquid diffuses into the bag. The indicator is yellow at neutral pH. The level of the liquid in the column rises as this change occurs.
And so you have a net flow into the bag, pushing that level
The pressure
up.
in the column forces some of the solution containing indicator out of the bottom of the dialysis bag. In this neutral solution, the indicator is yellow. When acid is added to the solution in the beaker, the indicator color turns to pink.
And so we can calculate the osmotic pressure. Again, you have the von Hoff factor, molarity of the solute, gas constant, and temperature in Kelvin. Again, nowhere do you see the identity of the solute. It's just the number of solute particles. And again, we're assuming ideal solutions. And so colligative properties are due just to entropy. Adding the solute particles increases the entropy of the solution, hence lowering the Gibbs free energy, making it more stable. And so that raises the boiling point, reduces the freezing point, increasing the range where the salt solution is the most stable phase. It lowers the vapor pressure, and again, osmotic pressure is just a colligative property. And so again, we can look at the phase diagram. So this is for pure water. Here is for the salt solution. And so again, it's increased the range where the solution is the most stable phase. I hope that helps.